Let us continue our discussion on grammars. In particular, the class of languages accepted by finite automaton can be expressed using something called regular grammars, which we can construct from the underlying automaton itself. We saw this case study a power n b power m. We observed that if you look at any of the productions, you will have something like state implies a symbol followed by, say, another state. So that is how it was for all of them. So such productions, if you look at it, you will always have exactly one terminal followed by exactly one non-terminal. And in fact, for all regular grammars, you will have this property. A non-terminal implies a symbol in sigma followed by another non-terminal. So this is non-terminal, and this one is also non-terminal, whereas this one is a symbol in sigma or it is a terminal. So this is how all our productions were. One can also construct directly without going through the automaton. If you go through the automaton, it is easy to construct. Okay. So let's look at this. The language is a power n b power m. We need a regular grammar. Remember, for any regular grammar, if you look at any production must be of the form a imply small a followed by this. This one is a symbol in sigma, whereas this one and this one they are part of n. Okay, so that's precisely our focus. Fine. Now, keeping this, let's attempt. If you look at any string, one has to kind of pump so many A's followed by so many B's. So what I do, I start with a symbol S. I say S imply AS. If you keep applying this rule, you get A imply S imply AS, then you apply AS here, then you get, so it's like this, you get AS, then you further apply this, you get AAS, you further apply this, you get AAS, like this it goes. And once I generate sufficient number of A's, then what I do, I switch to B, for which I use a different symbol. But I should ensure before I switch, I read at least one A, because the condition was n and m is at least 1. So it is S imply A followed by, say, B. Now with the help of the non-terminal B, I perform B power m. So I keep saying B imply BB. But remember, I should read at least one B before I stop. So I say B implies this. Fine. So now it's respecting our rule. Our rule says left side must be exactly one non-terminal. Right side it is a terminal or a terminal followed by this. Even this is allowed. A imply epsilon is allowed. A imply just a terminal is allowed. So if you look at this, for all of them, a terminal followed by a non-terminal or just a terminal. Fine. Now the interesting part here is any string of this form is generated by this. So what is our signature? Grammar consisting of non-terminals. In our case, it is S and B, and terminal is consisting of A and B, and followed by productions. These are all part of P, and start symbol is S, which means any derivation must start from this. Let's look at an example. Say let's take double A followed by 4B. Then we need to start from S. So S imply AS. Now I need one more A followed by, I should start B. So what I do, instead of choosing this, I'll choose this. So A, B, then I use this 3 times. Then finally I use this. So this is precisely the derivation for the string a square b power 4. And interestingly, any string of this type can be generated using this, and things that are not part of this, for example b square a power 4, such strings you cannot generate using this productions. So it is sound and complete. What is generated using this through a derivation like this is part of this, and every string that is part of this can be generated starting from S. Okay. So now this tells you that a regular language can be expressed using a succinct expression called grammars. Just like regular expression, they have finite set of production rules. With this finite set of production rules, we are capturing an infinite set. And in some sense, these formulas are recursive in nature, meaning you keep applying this, you get to generate a power n minus 1. Then go over here and read the nth a and go to b. With the help of this, you start reading m minus 1 b's, and mth b you read using this. So interestingly, one can come up with regular grammar for all languages accepted by finite automata. Now there are two ways. Either look at the language and generate a regular grammar, or when you know it is regular, construct the finite automaton, the underlying finite automaton, and from the finite automaton one can always extract a grammar. Fine. Consider this language, set of all strings over 0, 1 star having this property ending with 0, 1, 1. We know that the regular expression is 0 plus 1 star followed by 0, 1, 1. Now let's attempt a regular grammar for this. One can always get from the finite automaton, be it NFA or DFA, you can find one. So let me go through this, then followed by 0, Q1, 1, Q2, 1, Q3. Now you can see that from this one can write Q0 implies 0 Q0, Q0 implies 1 Q0 to take care of this. Q0 implies 0 Q1, Q1 implies 1 Q2, Q2 implies 1 Q3, and Q3 implies epsilon. Now for all these productions you find exactly one non-terminal. On the right a terminal followed by a non-terminal, or just a terminal or epsilon. Fine. So be it a non-deterministic finite automaton or a deterministic one can always come up with a regular grammar respecting the conditions. Now, independent of this, just by looking at this, one can always discover a grammar. So now let me start with S. Now we should read 0 plus 1 star before we go to 0 1 1. So what I do, I say 0 S implies 0 S or S imply 1 S. Now with this you can get 0 plus 1 star, correct? Because you keep doing this, you can get 0 0 0 0 S, again one more 0 S, and whenever you need 1 you use this. So with this you can generate everything. Of course you need a production to terminate, but this captures 0 plus 1 star. Now from this I need to switch and then start reading this part. Fine. So I say S imply 0 capital A, and capital A implies 1 capital B, and B implies 1. Fine. Now let's look at this. Each of them as a non-terminal S, A, B, and the terminals are 0, 1. Start symbol is S, and these are all my productions. Now let's look at a derivation. Suppose I need 0 1 0 0 followed by 0 1 1. I need to start with S imply 0 S, then I need 1. So this I'll replace with 1 S. Then I need another 1. This I'll replace with 1 S. Then it says 0. Then this I'll replace with 0 S. Then it says another 0. This I'll replace with 0 S. Then we get another 0, but the pattern starts. So I'll choose this. So from this I'll get 0 A, and 1 is replaced as A is replaced as 1B, and then finally it becomes this. So which means you get 0 1 1 0 0 followed by 1 1. Fine. So now here is another way of writing a regular grammar for this. You can see that this and this are structurally different. For example, there is one epsilon here, but there is no production rule that says epsilon. But they have some similarities. So this tells you that for a given language, just like automaton, one can come up with more than one grammar as well. Fine. That's one. Another one, because of say these three, Q naught implies 0 Q naught, Q naught implies 1 Q naught, Q naught implies 0 Q1, and so on. Is it possible that we obtain more than one derivation for the same string? Now, if you look at these three, if we need 0, then we go for this. If we want 1, then we go for this. If we want to switch, then we take this. So at this point in time, we may not see something like for a string, can we get more than one derivation? That may not be possible. But let me do the following. I slightly modify this and then add one more production. Say Q3 implies. So So you get to see Q2 implies 1 Q3, then this happens. So let me say Q2 implies 1. Okay. Now along with this, we also have this. Instead of saying Q2 implies 1, Q3 followed by Q3 implies this, and I am saying Q2 implies 1, but now I am adding this. So everything is part of our grammar now. Now production rules are precisely all of this. Now look at the simplest string 0, 1, 1. So I need to start from Q0, and now I need to generate this. So let me take this. So Q0 implies 0 Q1, and Q1 I replace by 1 Q2. Then there is a production Q2 implies 1. I'll use this. So this is the derivation, but one can also do this 0 Q1, and then it becomes 1 Q2, then it becomes 1 Q3, then it becomes epsilon. So we get this. Now you see that for this string 0, 1, 1, we have more than one derivation. So often one has to pay attention to things like this. So there may be strings for which we may find more than one derivation. It is possible. It is possible that the given grammar has this property. Okay. The interesting question is, can we always come up with a grammar, and the grammar has this property. You look at any string generated by this, it always has exactly one derivation. There is no string for which more than one derivation exists. Okay, so things like this one has to pay attention. Supposing you find a string for which you find more than one derivation, such grammars are called ambiguous grammar. And you don't find more than one derivation for any string, then it is unambiguous. So interesting question is, given an ambiguous grammar, can we always come up with an equivalent unambiguous grammar? So if you look at this, there will be some string for which you find more than one derivation. This says for any string you find exactly one derivation. So ambiguity is something we want to avoid when we look at compiler design, something called parsing. There ambiguity, unambiguity plays a role. We would be interested in designing unambiguous grammar so that there is a unique way of deriving a string which will help in parsing, and subsequent phases in compiler can answer certain questions if it follows unambiguity. Okay, so more about grammars and its relation to pushdown automaton, all that we shall explore now.